Hi, welcome to Module 6, Principles of Energy, and this should be a part 1 of probably 3 parts. We'll see where the recording brings us. We're going to be talking about solar energy uses, and we're going to start by talking about passive solar systems, so systems that are utilizing radiation of sunlight, but specifically in the forms of non-electrical use or non-electrical production. And then in the next part, we're going to talk about producing energy, trying to make electricity, or in an active system. So we're going to start passive solar, and then we're going to move to active solar. So one of the characteristics of solar energy is that it's incredibly abundant. And other than when our Earth spinning moves out of the circle of illumination, for the most part, we have a solar constant of 429 BTUs per foot squared per hour, which means that we have 10,296 BTUs per foot squared per day on average. And this is a world average, which means areas near the equator has a higher number. Areas very, very far north, near the poles, obviously a lower number, and specific areas, part of the year, they don't even see sunlight, right? If we're past the Arctic and Antarctic circles. One of the terms you'll run into is incoming solar radiation or insolation, not insolation, insolation. And this is referring to the sunlight specifically that makes it through the atmosphere down to the surface of the Earth. So now looking at that surface of the Earth, we can look at this lovely little image here, and we can see that there's this lovely spectrum of light curve and radiation measured in either a wave or in a particle, and you can see the wavelengths down here in micrometers written out, can be taken as gamma rays moving into the UV spectrum, so UV A, B, and C. The visible spectrum starting with your violets and moving all the way to reds. Then you get into near infrareds, middle infrareds, and thermal infrareds. Then you have up here your microwaves. Then you get into TV waves. And finally, way out here, we have FM waves. And then finally, on the very end of this curve, we see our AM waves, which means that if we want to maximize the actual energy storage of sunlight or taking advantage of sunlight, the part of the spectrum that we want to utilize or absorb will be in the part that is most abundant and makes its way down to the surface of the Earth. And that falls right into the ultraviolet, into the infrareds. So this is our spectrum that we're going to be taking advantage of. And everything we're going to talk about will fall into this spectrum part. And it makes sense. It's going to be the part that will be the most abundant and the most useful part of our spectrum. Which brings us to how to harness and where to look at orienting specific materials to utilize sunlight. So our Earth is tilted 23.5 degrees on its axis, which means certain parts of the year, sunlight is most directly overhead in the spring and fall. In other parts of the year, sunlight is most directly hitting the northern hemisphere's Tropic of Cancer. And in other parts of the year, it is most directly hitting at 90 degrees the southern hemisphere's Tropic of Capricorn. So in this image, we have a little house, and this is in the northern hemisphere. We know that this home is in the northern hemisphere because the sun is to the south of our location here. And we can see that based on certain points of the year, the angle of sunlight will be higher in the sky from our perspective. And so right here we have our summer months, and the sun is most direct on an angle that's very high. Here we have our fall and our spring months, and we can see the sunlight is centered. And then finally, in the lowest points from our perspective in the sky is our winter months. Now, if you're going to maximize sunlight, especially for passive solar, where I'm taking advantage of the thermal capacities of the sun, I'm going to want to maximize sunlight in my winter months and minimize it in our summer months. So when we talk about passive solar structures and orientations, that's what we're talking about. This is the same concept, talking about the positioning of sunlight, and we're taking it over the course of a day. Right, so they're showing you, and then once again, you can see that in our January or winter months, we have a minimum amount of daylight hours. So we really have to maximize our sunlight while we have it available. This table just shows us different cities, times of year, and the amount of heat capacity and latitudinal degrees that we can actually take advantage of in our sky. So possible uses of solar energy, it's about 2,000 times more abundant than coal, which means that it's an incredibly viable option. Right now, based on current technology, opportunities in locations with about 1/3 of all heating energy needs can be taken care of by sunlight. And this is with current technology. I don't have to do anything fancy or funky. I can just take advantage of what I have available. Variation throughout the year from the day can prove 0 to 330 BTUs per foot square per hour. And this is based on a Valhalla location. This brings me to when we're talking solar energy, it really has the capacity to sustain our energy needs if we could solve one problem, and that is the ability to store that energy. So what we're talking about is batteries. The technology is there to convert. We can take sunlight and we can make it into electricity. But once we have that electricity, we have to store it. And batteries are the tough part. But we're working on it and the technology is getting there. And who knows, maybe in a year or two from now, I will re-record this video and I'll be able to say, we have answered the battery problem. And now we're just, moving forward with this technology. But it's there and the capacity is there. And it's very viable. Which brings us to starting to talk about these passive systems. So this is a solar desalinization system. One of the biggest problems that we're looking towards in the future will be the ability to create clean water in locations that are either polluted or dirty or salty. So trying to create clean, fresh water. And one of the ways that we could do it is in a passive solar capacity, one where I have no electrical hooked up to it and I can just use the sunlight to take advantage. And so this is a simple passive solar system where I'm working on just containing the water down below using evaporation where I'm changing phase, right? We just talked about that in module 4. So I'm changing phase and I'm allowing that phase to change. It hits the glass surface, it recondenses on the surface, and then it'll drip down into this little trough structure that allows me to catch the purified water, leaving behind the contaminant or salt and utilizing UV and visible spectrum light as a thermal capacity to actually change phase and clean the water. Here's another example of a concept of solar desalinization. Once again, I'm utilizing phase change, passive solar, no active system here. And this one's a little bit more complex, and they have little cute squiggles to try to show evaporation because we need to be, cutesy about this, but that's another system. Here is the survival method. If you're ever on a stranded desert island, you can take advantage of the seawater to purify, and you're not going to get a lot of water, but you will get clean water that is fresh water that you can drink. And so, I have a container and a container, and my outer container has salt water. My inner container is the one where I can catch my fresh water, right? The evaporation happens. It sticks to the plastic. The plastic doesn't have to be clear. It could be an old black garbage bag, right? I can take advantage of that thermal capacity of the color black, same material as the clear plastic, but I can use the color black and use that. And then I'll just use the pebble to weight it to create that angle that I need for a location that the condensed water can drip to, become heavy and have gravity drag it down into the cup. Here is an actual working solar desalinization system. This one's the tank style with the plexiglass, and here's the trough structures. And then down here, you can actually see the little bucket collections here and the rainwater down over here for the structure. Here's another one. This one's small scale, and it allows you to put the water in over here. So this is actually the entrance tube on this one, and this is the exit tube. And here's another concept. So On that, solar ovens work on three basic concepts: concentrating sunlight into the device itself, converting that light to heat, and trapping that heat so that we can continue to build on the heat that's currently there within a little thermal greenhouse, right? We're creating a greenhouse effect within our trappings. We can do solar ovens out of anything. We can make it out of a flower pot. We can do it with plastic bags. If you haven't ever opened up a hot garbage bag in the sun, it is a stinking hot mess, right? So this is something that's a very easy build, but it can answer so many problems. And once again, it's a passive system. I'm not making electricity with that system. I'm just utilizing what is currently in place to take advantage and do what I need. Now, this is not a fast process. This is something I have personal experience with. I've utilized a solar oven, and especially when I was in grad school, and I remember we used to buy those Annie's burritos. We had the solar oven, and it's actually in one of these pictures. Let's see, right there. And we would stick those, we would unwrap them, and we'd stick them in here before we go to class. And then when we got back from class, our snack was ready, right? So this would be a little trick. And right here, you can see we're making a corn muffin in the solar oven. So popping back, this one, once again, we can see the concentrating sunlight into the system by using these mirrors or reflective surfacing, right? I'm trapping my heat within my system. And then within there, you can actually see these are like a painted black box. You can see this is an insulated black box. We are creating a system where we are converting any sunlight that's in the box into heat. So I'm using a thermal capacity. Here's a reflector system, sun tea style. If you remember back in elementary school where you'd look at diffusion by taking a container of water that has a clear pot and you put the tea bags in, you bring it outside and you watch it diffuse as it heats up, right? So we're creating a little reflector. Here's another really simple, just using reflectors to create a solar oven system where I can cook. Here's a box type. This is the pizza box style type. And then once again, this is the one we have at the McCoskey Center. This one was very serious. We were using it to cook food that we required to eat. So this was very purposefully built. Once again, both of those systems that we just talked about is passive solar. Now we're going to talk about passive solar in a home. So orienting and arranging and using things in your home to create thermal capacity so that we can convert that light to heat to take advantage of what we need. Passive solar homes that are built can save as much as 50% on heating costs, and that is a 1 to 5% increase in construction cost overall. Can do this simple maneuvering. Now I know we live in an area in Valhalla where we are retrofitting homes. We are not taking something that is a new build. So we don't necessarily have the passive solar capacity in the home that's currently built. But that doesn't mean that we can't do things within the home, remodeling style, to take advantage of solar capacity within. Here is the picture in the book that's showing us a high performance home with lots of windows. If this is in the northern hemisphere, we know that these windows would be south facing, right, to take advantage. And then once again, you can see the tiling on the floor. The tiling is important because these tiles will have a better ability to conduct the heat energy. So it's going to be absorbing that sunlight. And then in the evening, when the sun goes down, I'm going to want to close the drapes to keep this area warm and allow those tiles to share the heat energy that it's been absorbing all day long with the rest of the room. This is a picture that's showing a home that was built in a passive solar style inside the town of Concord, New Hampshire. And it's showing you that inside the home, its ability for capacity of heat, and outside what the temperatures were at a given time. So over the course of the day of January 25th to 26th, we can see that it was pretty warm in the afternoon, and we can see that the home just begins to heat up, right? And then it's holding on to that thermal capacity throughout the evening, because here's midnight, right? And then by noon the next day again, we can see that it kind of maintained its curve of heat at a certain baseline, right? So there's an ability for these homes to maintain heat within themselves. This is a concept called a Trumby wall. Trumby walls are using a structure that's not blocking the window itself, but it's up near the window where there might be some footage of space between the window and the wall that allows us to absorb sunlight up into the actual structure. And so we can use different things with thermal capacity. They could be concrete, they could be structures that are made out of stone or some type of tiling. There's art pieces, and now we've even seen Trumby walls that are fluid. They're called fluid Trumby walls, and they're using capacity of these water tanks that are very attractive. Now think of a big building, like a standard commercial building structure where you have windows that are just pouring all the sunlight in, and it's such a pain. And so what do? We put up blinds to try to block out the sunlight. Instead of that, let's take advantage, reduce the heating that's necessary for the building, and put Trumby walls in to the structure and allow us to just absorb that sunlight. I mean, for the most part, somebody closes the blinds and they don't get opened again for months and months and months. So, take advantage of the system that's there, and you can do something very sustainable with the capacity that's present. So here's some example of Trumby walls. Once again, it's not blocking the window itself, but it's very close to the window. And so here's some Trumby walls, right? And this is in an office style construction where you do not want the sunlight really in the building because it's just creating too much glare. This one is a Trumby wall that's quite purposely built to be attractive, and so you can see that the windows go all the way down, but the wall is here as a little walling structure within the home. And here is that fluid Trumby wall that I was talking about where they're using water tank style, and that's very attractive, right? So there's a measure to be made, a sustainable practice that's being built on that one can take advantage of, and ways that you can experiment and be quite creative within a space. Talking about old systems of using energy, one of the early uses of creating hot water is these structures where we actually heated water. And the Egyptians were doing it, and then the Romans also picked up on it with bath structures. And some places didn't have the ability to find a hot spring, right? So they didn't have a hot spring available. Instead, they created warm water by creating these troughs that they then put metal tubing within, and the metal tubing and the trough absorb the heat, and they actually would disperse it into the water as it trickled past. So that's one way to heat up your water. Looking at a passive solar home design, this home was built to be passive solar, and this is actually a place called Taraday. It's in Prospect, Pennsylvania. And this structure is built so that there is a window set along the top, like an extended greenhouse on the structure itself. And inside is the flooring that has thermal capacity. There are windows in between, and even though this room is an indoor room, right? This isn't a greenhouse, this is an indoor room in the structure. There are windows so that if it's really cold and I'm not getting good thermal capacity, I've had a lot of days of cold weather, I can shut out the room. Also in the summer, when I do not want to share the heat that's building up in this room, I can shade out the room, close up the room, open up the windows, but then close out the house and shade out the house. And so this little extended room is acting as almost like a little attached radiator, taking advantage of the sunlight within itself. Now, if the weather is really good and I want to take advantage of the heat and it's winter and this room is nice and warm, I then open up all my windows and doors in my little structure over here, and I let all the heat into the house. And this is an example of what this would look like. Now, this house would have a lot of open cathedral sets within it, or little jump rooms, or areas that have overhanging lips. Little princess balconies in other parts of the house to allow the heat exchange through the building. And then the other key part about the building is that there's somewhere for the heat to escape in the roof, because the warm air will be less dense. It'll be at the top of the surface, and so I will have some place for heat to escape. So on that note, we'll talk a little bit about passive solar home design buildings, and then we'll start talking about how to make a passive solar shower. Through these four main categories within passive home design, and then we're going to jump past the slides with the definitions. If you would like to look at the definitions, please take the time to read because they are available to you. So passive solar design are working on 4 basic concepts. One is proper orientation of windows or whatever surface might be your open surfacing, the surfacing that you want sunlight to enter through. Then thinking about when that sunlight gets through, what is your thermal mass? How are you going to take that sunlight, absorb it, and convert it into heat energy? So what do you have that's a conductor? Right? Distribution mechanisms. So are you opening up the floor plan so that there's an easy way for air to move around? And then is there some way to get the heat to escape to keep the home cool when it needs to be so? And then control strategies. How am I keeping everything moving around the home? How am I orienting this house to make it work for me? What are my controls? One of the simplest controls that people forget about is silly things like orienting your roof so that you maximize sunlight in the winter, so that the lips or overhangs or angling of the roof structure allows sunlight to enter through the winter when it's low in the sky, right? So my angle of my home and the sunlight can get right in. And then that angle will block that sun from getting in when the sun is high in the sky up here. It won't get past the roof structure. So passive solar home design is maximizing sunlight in my cold months, winter, and minimizing sunlight in my warm months, my summers, right? So I'm getting things that are appropriately angled and built to the proper structure. So once again, these are my explanations of those 4 concepts. Read through them as necessary. And let's ooh and ah a little bit. Here is a home structure. Here is the basic layout of that home structure within itself, right? And we're maximizing sunlight. So this is an orientation to the south in this case, and I'm taking advantage of the sunlight. And I have good angling of the roof so I can block out the sunlight I do not want in the summer months, but I can maximize it when the sun is low in the sky. It can get right in my winter months. Once again, good control and ventilation systems within it, right? So this is my structures and how I'm getting my air around. Some more ooh and ah. Here is the attached greenhouse concept, where this is an extension room on the house, but allows me to maximize or use this like a little furnace that I can then open up all these surfaces and let the heat into my building when I want the heat to enter. And when I want to block that heat out, I can close all these inner surfaces and block the heat out of my thermal home. Here's one that's talking about that angling of roof structure to make sure I'm maximizing sunlight. And it's just gorgeous. Ooh and ah. And then this one's just such a fun concept piece, but same thing. And this one obviously has nice even flow where I have a little princess balcony that overlooks. So I'm allowing the air to circulate through. One of the structures that has excellent roof circulation is the shape of a barn. A barn's roof structure is one that's built to allow good circulation of air maximized within its facility, which is why barn structures were built for areas that we were not going to heat or control heat in, and we did not need private rooms for. And so we would build these structures to allow the air to circulate, but also to allow something like the big animals, the horses and the cows, that are providing a lot of body heat themselves to heat the building and assist these smaller animals, which might be in the rafters like chickens, to be warm as well within the structure. So that structure of a barn has excellent circulation on itself. So it allows me to ventilate or create controls within heat structures, right? So refining the design. There are simple things that one can do to refine a design and make the home really work as a passive solar structure. Some of them is to insulate and to have air sealing. I want to seal up all of my leaky surfaces. I don't want anything to leak air without me being able to control it. I want to determine when air should leak. I want to be able to open the window when I want air to come in and out. When the window is closed, I do not want the window seams to be leaking, right? Window location, glaze type. Windows have a lot of options nowadays. I can glaze out sunlight that I do not want. If I have something that's facing the south and it's just gaining too much heat energy because of its angling and I'm getting too much in the summer months, I now have the option to glaze or shade out my window, right? Thermal mass and location types, think of things that are excellent conductors. They're good at absorbing heat energy. They're not good at holding on to that heat energy. which brings in the idea of maintaining heat within a surface, which also brings up if I have a floor that happens to be tile, so it has a lot of ability to conduct heat through it, I'm sharing the heat energy with it, I can do something like put a rug down in the winter months when I do not want to be sharing my heat energy because it is cold. And so I can do things to maximize the properties of a room. You can do things like seasonal. If I have a room and I want a rug down, I can change. I have the same material, but I know that black will absorb the entire spectrum of light. So in the winter months, I might bring in a black or dark colored rug to maximize the amount of sunlight absorption and transference to heat energy. And then in the summer months, I might lighten up the color of the rug and select something that's a white or a light color, very, very mild sky blue or something, to change out what I'm receiving in sunlight, right? Same material, but they have a capacity for absorption of sunlight that's very different. And then the final part to think about in redefining our design is auxiliary heat. What am I doing? Am I auxiliary cooling? What systems am I using in this home to really maintain the temperatures that are currently balanced in my design? 3 ways to design a passive solar home. Indirect gains. This is where I'm using things like south-facing windows to take advantage of my heat and its ability. Direct gains, these are some type of structure or some type of thing I am adding onto my home to maximize my heat energy, whether it be that indirect gain by building that little greenhouse type structure, or putting in a Trumpy wall, or am I putting in some type of thermal mass item that's taking advantage of heat. And then finally, insulated gains. These are ones where I'm creating bubble or thermal rooms. This is my sunroom, my attached greenhouse to the home, my structure that I'm going to add on the side. I've seen somebody who's doing an experiment with like kind of like these black rain barrel things that are doing catch of sunlight. And so they're collecting the air and then they're opening up these barrels that are like attached to windows. It's a kind of a bizarre concept, but it makes sense. They're taking and they're heating up air in these barrels, and then they're opening them up and using them as these heat little oven kind of structures, allowing the home to be heated during times of cold. It's kind of smart, but they are storing it up for evening, and that's the way that structure works. But that would be an indirect gain. Some more passive solar design, just gorgeous. Look at the thermal mass on that, right? And this is kind of a combo where they're doing this little structure. And I actually know what this home is. This home has a gray water system. So this is a gray water system where they're recycling the non-sewage water. So this is like things like shower water or dishwashing water, right? So they're using that to grow. Another beautiful one with thermal mass down below. Another structure with thermal mass, and this one has sunshades on the roof. This is blocking out the sunlight from getting in the summer months, but it pulls back for the winter months. It actually slides back, so it slides up here and allows the sunlight in. Another beautiful structured home. This one's big and open. Once again, flooring is granite, so thermal mass. Gorgeous, right? Now we're going to talk about some active systems. I'm going to start out when we talk about heating of water, because we want to be able to bathe, right? We want hot water in our world. And so we're going to talk about 2 passive hot water systems and then some active hot water systems. This is a picture of a home that's inside your book. And right here, this is the actual solar panels. These are solar panels, and I can tell that they're solar panels because I can actually see the circuiting running, right? This is flat plate collectors. These are hot water heaters. This one on this side. So residential private use solar energy, passive and active systems. Just a little bit just talking about the book, chapter 6, radiant energy. Once again, just looking at different text and advantage. So we're going to talk about heating your hot water, and this is your standard hot water tank. This is an 80-gallon tank, and I know I snapped this picture back when I was on the other coast in California, and I know that because I have my earthquake straps on my hot water heater. So, you know, some simple things that you can do to save some energy on your hot water is to turn the water down to 120. If your hot water heater is above 120, unless you're doing something where you really need to clean something at very high temperature for some type of health issue or some reason or other, you really don't need your water to be hotter than 120. So just turn it down. Turn it down. You're wasting a lot of energy. Another thing that you can do is hot water tanks have insulation. It's a tank with an outer layer of metal that has insulation in that outer layer, but they may still be leaching a lot of heat energy through it. And if so, they actually make a little tank blanket. It's this little fiberglass shield blanket that's enclosed, and you just kind of tuck it around. It has Velcro, and you just Velcro it on, and you can put a little jacket on your hot water tank and keep the heat in so that it doesn't have to work as hard when the thermometer turns it on to heat up the water. And the other one is to do stuff to just restrict the amount of water that you're utilizing and yet create the type of pressure that you enjoy. A lot of people enjoy a good amount of pressure on the water as it comes out of something like a faucet or out of a shower head. And so doing things like putting in low flow, but allows a good amount of pressure for water. If you went and found that hot water tank that I told you to go look at, and there was no tank at all, there was this funky box, you have what's called a tankless hot water heater. These are incredibly efficient, but also incredibly expensive systems that flash heat or rapidly heat the hot water at the moment that you're going to use it. A lot of these systems require that you turn them on ahead of time, and so you have to flick them on and give them like a half an hour to heat up to get working, but they heat up the water kind of instantly or as needed for you to utilize with hot water. And those are your flash system tankless hot water heaters. Now let's go back into the world of solar and talk about passive solar hot water heating systems and then an active system at the end. And so we're going to talk about the batch hot water heater system, a passive version where I'm using gravity to heat my water, and that's a thermosyphon system. And then finally, we'll talk about the active systems. These are products that you buy. These are flat plate collectors. Batch hot water heater systems are the build-it-yourself, reuse an old hot water tank to make a hot water heating system. And they work basically as such, where you go and you get yourself a hot water tank and you build what's called a bread box to put it in. And that bread box has good thermal capacity where it will trap sunlight, convert that sunlight to heat by painting your hot water tank surface black and allowing that to heat up the water. It has been a system that has worked for multiple amounts of years, and if you have the right structure and the right home style, you can take advantage of heating your water in a passive way or just bump your current hot water tank to allow it to have that little bit of extra heat. Think about it this way. If I can take advantage of the water coming out of the faucet at about 55 degrees Fahrenheit, and I can heat it up to 120 and then circulate it into my indoor hot water tank to make the difference in my heating, I might not have to heat it for a lot of the year. And then in the winter months where I might have to heat it up a little bit, I might only have to heat it up 20 or 30 degrees instead of having to heat up my hot water by 40 or 50 degrees, maybe even 60, 70 degrees to make it more comfortable to utilize. So determining your tank size depending on what you need. For the most part, you're going to go out and get an 80-gallon tank. If you have your standard 4-person household, you're going to go get a 40-gallon tank to take advantage of your hot water needs. Let's say you have yourself a lake house or remote house facility. You could build yourself a hot water heating system, take advantage of that so that you don't have to take cold showers, right? So it doesn't have to be something that you're using on your home, but you can just make the other parts of your life more comfortable. So this is a design, and I'm going to just kind of flick through. This is stuff that you could take time if you're interested in doing it. I've built 3 of these systems now for fun use. One of them's hooked up to my uncle's house because he's an awesome groovy dude and he lets me do these things. But this is basically different design structures. This one I love because I'm taking advantage of my batch system. So I'm taking out my exterior of the home and I'm just drilling through the wall and I'm actually attaching it to my already existing hot water tank in my home. So the way it works is I'm running my cold water line out of the house and I'm attaching that to the tank that I have peeled off the outer layer of and painted black. I'm attaching that to the cold water line on this tank. Then through the hot water line of this tank outside, I am running it in and attaching that to the cold water line on this side of the tank, right? So now what I'm doing is every time I'm pulling water from here and I need to refill, this is pulling water from this tank. And as this tank gets empty, it's pulling water from the actual cold line. So I'm constantly heating it up, maybe up to 100 degrees, and then I'm taking advantage of heating it up only another 20, right? So 55, heating it up 45 degrees, coming in here at 100, set to 120, 20 more degrees, out the line. A lot less energy utilized in this sort of build. Another little structure. These are all concept pieces. Take your time. And then this is me doing a build, right? So this is the one at my uncle's house over here. This is a picture I stole from online. And here is me building because, you know, got to do it. So I went and I made sure that I had a tank that had good water retention. I cut off the exterior aluminum lining of the tank, peeled away all of the insulation. You can see my insulation right there. That was in between the two tanks, and basically exposed it. Then I built a nice insulated box for it to go into, painted my tank with Rust-Oleum paint on the exterior, and then I just hooked up my lines. Yep, I ran them up into the house and hooked them up, and I'm good to go. Now, this system is located in the local Stamford area, so Stamford, Connecticut, and we use it for part of the year, but once we start to get to temperatures below freezing, we just close down the tank. We actually drain it, because we're not going to try to use any type of fluid system. It's an open system that allows us to take advantage of the heat energy. And so we drain it so that it doesn't crack in the winter, and then we use it in the spring, summer, and fall. Passive solar systems. If I take that bread box system and I do not want to put an active pump system on my hot water heater, I can take advantage of using gravity. And so this is just a gravity feed shower where we have the water and it's being hand delivered. So I'm actually putting the water into the tank and then I'm allowing it to gravity feed into the home. And that's what a thermosymphone system is. There's no pumping or electrical mechanism hooked up to it. It's based on gravity feed. And so I'm going to introduce you to that term and just show it to you so that you can see it. It's a batch hot water heater system using gravity feed. And so here's the double batch, once again, exterior batch system. And here is that blow up of that picture with the thermosymphone. Here is another version of that. And I like these a lot better. This is the one I have in my yard. And I use it in the summer months. It's really nice. It's really nice. It's kind of fun. And I just bring the hose up, fill up my tank, allow it to heat up, and then I run it, and it's just gravity feed. And it gets some pretty good pressure. Sometimes it's a little too warm, and so I end up taking the hose and running it down, and I end up turning on my hose, and I use the cold water at the same time that I'm using the hot water in the tank because it's sometimes very efficient. This beautiful outdoor shower system over here is another thermosymphone where I'm heating it up outdoors and using the gravity feed. And then this one I just thought was funny. Now, this was just genius. This was in one of those ecology online websites, and I was like, why did I not think of this beforehand? But this structure is using black hosing to take advantage of hot water heating within the system. Isn't that just genius? So it's a thermosymphone again, but I'm just taking black hosing. It has a lot more thermal capacity, right? So smart. Which brings me finally to the point we're going to talk about active flat plate collectors. And so this is our flat plate collector heating system. These are products that I'm purchasing. Your typical flat plate collector is built on a metal box style with some type of plexiglass or glass covered sheeting with a high thermal capacity opaque black glass on the front. It allows us to transmit heat. If for some reason there seems to be an issue with your flat plate collector, oftentimes what's happened is that the tubes that are running the water or the fluid, if it's just a fluid slurry, like in our climate, we might buy a product that has a non-toxic fluid, inside that is got an antifreeze so that it does not freeze in our collector system, and it goes through thermal contact within our hot water heater within our building. But if I'm finding a lot of inconsistency, what's happened is the tubing has lifted off the insulator plate. And so that's one of the places where I'll see efficiency go way, way down if for some reason those two things lift off of one another. Here is an example of the mounting of a solar hot water heater system. Here is the interior box structure. And then here's some arrangements. And because this is a product that is purchased, there is a lot of different product versions that are out there. And so we have the serpentine parallel tube. This is the tube form in sheeting and the trickle type. Serpentine and parallel tube are tube structures that are running on top of that insulator plate with an opaque glass on top of that, within a thermal box, a box that has good insulation structure. It has an intake valve at the bottom where I'm sending the cold water in, and an outtake valve at the top where I'm pulling the hot water out. It works on twofold of the pressure running through the lines in the glass, as well as siphoning off hot water that's rising within the water itself in the tube. Some images. Flat plate collector. This one is going to a hot water heater. Here's a corrugated. Corrugated is a surface run system where I'm actually just running the water down the corrugated sheeting, which allows it to heat. This is something that works really well in tropical climates and also doesn't require a lot of work or money. It goes all the way back to one of the earlier module videos that you watched in part 6, where I showed you the aqueduct system with the piping, the copper piping that ran inside, and I said this is one of the ways that we could heat water. This is another way I could heat water and create also a really attractive water feature. Which brings me to the newest version of hot water heating on the street, which is the evac tube. Now, there is a demo evac tube system that is located in the quad in the tech building of WCC's campus. And so if you are walking through the tech building, look in the center of the quad, and you'll see this funky tubule structure black things out there. Those are evac tubes. That's a hot water heater system. Here are some examples of evac tubes, and they are a tube-in-tube structure where we send the cold water down and into the structure. It allows the hot water to raise up because it is less dense, and then I siphon the hot water off the top. So I'm basically syringing in the cold water to the base of the tube and allow hot water to rise to the top. They are pretty efficient at heating up your water. They do a really good job, but they're incredibly delicate, and a lot of things can change their ability to create thermal capacity within themselves pretty quickly. So slight loosening. Here's a picture of an evac tube structure in a demo model at some workshop. I take pictures of everything. This is a solar plate flat collector that is a closed loop system, and it's closed loop because it's a fluid that is being run through its tube lines, and it just keeps running through the fluid structure here, and it goes in thermal contact with the water, but it does not actually mingle with the water. So the tube is heating through the tube structure, so through the copper itself, it's heating through it to the water, right? So I'm in thermal contact, but I'm not in physical contact, where the fluid in the line is touching the water in the box. And this is important. This is one of the systems that you would buy or use in our climate type up in New York. We would want to use something like this where we wouldn't have to try to drain the system or worry about it freezing or cracking in the winter months.